Hi, my name is Tova, and today I, along with my colleague Johnny, will be presenting on our project, Mapping the World's Offline Population. This project was coordinated over the summer through the Data Science for Social Good Fellowship at the University of Warwick with a team of data scientists and mentors whose names are listed here. Our project partners were the International Telecommunications Union, or ITU, along with UNICEF, both agencies in the UN. They've collaborated to create Project Giga, which aims to connect every school to the internet by 2030. Today, 2/3 of the world's school-aged children have no internet access at home. The lack of connectivity for children doesn't just limit their ability to connect online, it prevents them from competing in the modern economy, isolating individuals and perpetuating the digital divide. Less than 1 in 20 school-aged children from low-income countries have internet connection at home, compared with nearly 18 in 20 from high-income countries. COVID-19 has exacerbated this disparity as children relied on the internet for their schooling. And for children who lack internet, that means they've not had proper schooling for the last year and a half. We started with the data given to us by our project partners in Brazil. The data was a survey done by their statistics office that had information on a specific amount of census tracts in the country that measured to a weighted average. The data was flawed because it was only given to us in an aggregate and not by exact location. The surveys also only happen every couple of years and only for some areas of the country. Additionally, it is important to mention that internet access here is defined as any way people get on the internet, so either through Wi-Fi or broadband, and also as a measure of if they have a device to get online. So the survey data could only get us and Project Giga so far. In general, as we mentioned, ITU only knows internet statistics on the country level based on survey data, which is often of inconsistent quality. Our project builds a toolbox for getting connectivity statistics that are more current, granular, and accurate than previously. What used to take months in working with individual countries to collect local survey data can now take a matter of hours with our tool. And it's also cheaper. Our tool outputs a priority list of schools that need internet connection, with an emphasis on the amount of people that would benefit from each school. And why schools? Because these often serve as community hubs and places of learning. Our second goal was to use the local area internet statistics to determine national or province level statistics for countries not currently mapped by ITU. For our project, we gathered and trained a model on Brazil schools, and then used this trained model to predict for schools in Thailand and the Philippines. First, we had to determine what might be helpful in indicating if an area around a school has high internet connectivity. We came up with a few open source data sets. The first is Ookla speed test data, a good indicator for how fast the internet is running in certain areas. Then cell tower data, helpful in indicating where mobile connectivity is located and if schools are within range of a cell tower. Next, population data, which is helpful in having accurate population numbers. And then Facebook user data. This works by showing how many users are within a 5-kilometer radius of any school. Of course, there are issues in places where Facebook usage is not high. Lastly, we have satellite data in 3 different forms. Nighttime lights shows areas with lots of light and presumably high levels of internet. Global human modification is a data set created by engineers by combining many different indicators. And measuring vegetation is our last data set. The assumption is that areas with higher vegetation are more rural and have less internet connection, while areas with low levels are more urban and have higher connection. Nighttime imagery, global human modification, and Facebook users prove to be the most important features powering our model. And why are these specific predictors so important? These data sets are continuous, meaning they don't stop at a certain spatial scale or boundary. They're globally ubiquitous and standardized. Calling this data for school buffer zones can work for any school in the world, and it doesn't contain the human error that survey data does. We then trained a model that extracts patterns from the data. On average, our predictions are only 5% off base, provided here as the mean absolute error for easy interpretation. Our metric is particularly appropriate because we built it to focus on the schools with lower internet connectivity.
And now with that, we can delve into our modeling processes. Firstly, I'd like to highlight that we experimented with treating the prediction of offline populations as both a classification task and as a regression task. And this was thanks to helpful feedback from other fellows and mentors throughout the fellowship, who recommended that we experimented with classification after first treating the problem solely in terms of regression. Our best regression models outperformed our best classification models, and regression average errors indicated superior performance to classification accuracy results. The other benefit of regression is that it gives continuous predictions, meaning that we could have a prediction for a school in any range from 0 to 100% connectedness, rather than having to discretize this scale into, say, for example, low and high, or 0 to 10, 10 to 20, and so on. And here are how the model classes we experimented with performed relative to one another. XGBoost was our best performing model, followed by random forest. And support vector machines and neural networks performed significantly worse, with linear regression being unable to learn any patterns in the data at all. Neural networks likely didn't perform well because they deal better with raw sensory and high dimensional data rather than the structured data that we were feeding the model. We mentioned the custom metric, and this worked by creating an error function that only compared for low connectivity schools, which we defined as those with less than 30% connectivity. And this only slightly reduced performance in medium to high connectivity schools, which was a trade-off we were happy to make, given that focus on low connectivity schools was much more aligned with our project goals of getting these schools connected to the internet. Here we have a scatter plot of our predictions against the ground truth for Brazil. The green points are these proximal to the ground truth, while the yellow points indicate a more erroneous prediction. And the over-predictions for the low ground truth values highlight the importance of our custom metric, which optimizes performance specifically for these low connectivity areas. We note that the series of ground truth ones on the far right-hand side stands out, but we chose to not to neglect these values, as it seems feasible, given our conversations with the Brazilian Statistics Office that conducted this survey, that there would be such a number of areas with 100% connected survey respondents in Brazil. And here are our feature importances for the XGBoost model on Brazil. For those unaware, these measure the relevance of a feature to the model's predictions and performance. Here we present this as the dropout loss, which provides a measure of the additional error that you get when you remove the feature from the model. Our best performing feature was the average mean radiance. So this is a satellite imagery data set and highlights the importance of our satellite data set use on the whole. The third, fourth, and fifth best performing features were also satellite data sets, which is really interesting because conversations with our project partners at the beginning of the project indicated that they and their domain knowledge assumed that these wouldn't be particularly relevant data sets. The second most important data set of estimate MAU is the monthly active user estimate from Facebook. This was expected to be a high performing feature, but again, we want to emphasize how assumptions on how these data sets would perform didn't necessarily align with the final results. As for example, speed test data seems like an intuitively relevant feature for predicting internet connectivity statistics, but here those are our two worst performing features. And finally, we can take a look at our model's predictions. Here are the absolute online population predictions for Brazil. So each point here is a school location, and the green points indicate higher internet connectivity, and the low points indicate low proportion of the low absolute online population. And with this, we could then be confidently deliver our priority list to the partner and be done with our job. And this priority list is a rank of the schools in terms of offline population, i.e. the population that would be served by an internet infrastructure project in the region. But not so fast, because we also want to see if this works for other countries.
We used the same model to predict school connectivity for Thailand. This map shows every school point in Thailand and its predicted online population, and it seems sensible both as school points and as aggregated provinces. However, we cannot quantify how well we did because of the inconsistent quality of the survey data. What we can say is that these are the schools and provinces that need to be prioritized and where internet connection is most needed. We then applied our previous model and also trained a new model using the Philippines data. The average connectivity from the applied Brazil model is 60%, while the retrained model suggests 30% average connectedness. We found that the retrained Philippines model fits more accurately to the Philippines survey data, But the survey was conducted in 2019. And after discussing with our partners, they feel that the applied Brazil model is more precise with the current state of the internet in the Philippines. So we had many limitations when building our project as we only had 3 months. One of our limitations was the extent to which we were not able to include spatial components in the modeling process. This includes geographically weighted regression for measuring school internet connectivity, as well as spatial cross-validation to check our results. Additionally, we made a priority list of schools for each country and ranked based on how many people it would impact. However, many of these schools have overlapping catchment areas, and therefore, once the first school on the list is helped, it might reshift the next school in the list because the first school also helped people in the next school area. Because of this, we were concerned aggregation on an absolute level would inflate the population of people, and so we shifted between absolute and percentages throughout the project. Our next step is to explore how training and combining different models might give us further information on the validity of our predictions. First, we start with Brazil, and then we move to Thailand, and then the Philippines, both using one model to predict for another and also retraining the models. Perhaps then we can see this as a group. And then we use all these models to predict for other countries. One step for the project was to create regional models for different areas of the world, or clusters based on country-level indicators like income or government structure. Eventually, we hope our model will be robust and generalizable enough that it will not depend on the survey ground truth data at all. Lastly, our impact. We created a methodology which can be used on any country in the world to assess their internet statistics in a more timely, accurate, and granular fashion. Our toolbox of scripts will be able to support evidence-based policy that will bring internet access to schools and communities throughout the world. In this way, we all win as we minimize the digital divide and prepare future generations for success in the 21st century. Thank you.
Hi there, Tova.
Hello.
Tova and Jonathan, that was a wonderful presentation. Thank you so much for sharing your impactful work that you're doing. For our Q&A today, we are also going to be joined by Robert Hager and Jacob Beck. So welcome.
Hi.
So we do have time for a few questions here, and it seems like you answered one of them at the end, but just want to confirm. So someone asked, is this analysis geography agnostic? And it seems like that is the future goal for this model, correct?
I'm not really sure what the person means by geography agnostic, but I would say that we are trying to be able to use it for countries throughout the world. So it shouldn't matter if there's information on a survey level data for a country.
Gotcha. Yeah, I think they just meant, could this be used for any geography? So that makes a lot of sense. What other use cases could the model you used be applied to?
I mean, given you would want to predict any other, I don't know, aggregated metric on how many smartphones are used in a certain area or how many cars are used in a certain area, and you would get survey data for that, you could take the same approach to predict those target variables with the given satellite data and so on we used. So I don't know if this answers the question, but
I think it does. Does anyone else have anything to add there?
So a lot of our work was just trying to identify the schools and the communities that had low internet connection. And I think the future kind of like use cases for this work is then identifying where exactly to put the infrastructure and also like how to give out devices on like a different kind of like logistic level. So this was more of like the large scale level. And I think a lot of the future use cases for these models is like how to create the logistics behind it in terms of giving out the supplies and materials.
Absolutely. Thank you for that extension. I think we have time for at least one more. So you explained perhaps why you chose regression over classification, but how does your model perform compared to other benchmark models?
So actually, the kind of the
biggest challenge, I suppose, with this work, and the main premise was that it's new. So there aren't really many systems against which we could benchmark for the prediction of offline populations using survey data as ground truth. So really, I suppose like the measures to the benchmark is that this is one of the first such models that use these machine learning methods that have been used in so many different applications in this specific use case.
Gotcha. Thank you. Yeah, it sounds like this ground survey data is a huge differentiator for your model, so that makes a lot of sense. Last question, kind of around use cases again, but can we take the same approach to predict information about third world country or remote places, for example, where food deserts are?
I think like definitely this is within the same goal in terms of like how to collect granular data using like satellite imagery or Facebook API and things like that. Obviously, you need other ground truth data and to work with somebody on like what the food desert indicators are or like what the numbers are. But definitely, I think that the same methodology in terms of collecting the indicators would work. I don't know if my colleagues have anything to add.
Yeah, not especially. I guess it might be more difficult to find data sets that serve as a proxy for example, yeah, like whether or not, food deserts, because with internet usage, you can use lack of electricity, lack of Facebook users, these like very obvious things that you would indicate with internet usage, but food has less of a digital stamp in an obvious sense from which you'd be able to find features that you can feed into a model. But yeah, I'm not sure.
Absolutely. So we are up on time here, but thank you again, Tova and Jonathan. I'm really excited to see where your work goes and how the model continues to evolve to spread to other geographies and further your impact. And Robert and Jacob, thank you again for joining us for the Q&A today.
Thank you so much.